Okay, so in this video I want to talk a little bit about the central limit theorem. I'm just going to start off by looking at a population distribution of, let's say, the heights of people in a particular country. So this is how the heights of people are distributed in a country. It's normally distributed, and let's say the mean of the entire population is 170 centimeters. So we measure the heights of every single person in the country. We found that the mean of every single person in the country is 170 centimeters, and we find that it is normally distributed. So the mean, if we've measured every single person, we've taken the mean of every single person's height, and we have found that it's 170 centimeters. Okay, so now let's say we go along then and we decide to take samples of the population, and let's say we take samples of size 50, for example. So we go along, we take 50 people, randomly selected 50 people, and we measure their heights. And then we find, from that sample, we find the mean of that sample. We will find that the mean of that sample will be somewhere around 170. If it's taken randomly, it should be somewhere around 170. So if we take another randomly selected sample of 50 and find its mean, we should also find that it'll be somewhere around 170 centimeters as well. If we go along and take that, say 1, 2, and we keep doing this over and over again, we keep taking the means of these randomly selected samples of 50. If we keep doing that until we've taken every possible sample, different sample, randomly selected sample of size 50, and we take the mean of each of those samples, what we'll actually find is that when we look at the distribution of those means, so we're going to look at the distribution of the means, we'll find that those means will look something like this. Okay, so we'll find that the distribution will be a lot narrower, of course, than the original population distribution, because most of our means here are somewhere around 170 in this case. So the distributions, there's going to be much less of a spread. But what we will also find, in fact, is that the mean of our sample means will also be 170 centimeters. So the sampling distribution of our sample means will look like this, and the mean of our means, if we take the mean of all these means, we should also get 170 centimeters. But you'll notice here that the spread is different, as I said earlier. This spread is much narrower than this spread here. So the standard deviation of this data here will be much less than the standard deviation of this data here. So this is, the standard deviation here is just given by this symbol here. The standard deviation of our sample means, is given by this formula here. Standard deviation divided by the square root of n. This here is the standard deviation of our population. This here is whatever sample size we took. In this case it's 50, so we would write down whatever the standard deviation of our population is divided by the square root of 50 in this case. And that will, this formula here will give us the standard deviation of this distribution here. Is the standard deviation of our sampling distribution of our sample means. So this here is called the standard error. This is called the standard error. So the standard error is the standard deviation of the sampling distribution of our sample means. This here, this sigma here, is just standard deviation. That's standard deviation of our population. So both are standard deviations, but this is for the population. This here is for the sampling distribution of our sample means. Okay, so let's just summarize that, what we've done. We have a population, and we've got a whole series of samples. Now, our population has a mean of mu, so that's our mean. our sample will have a mean. This is our sample mean, which actually also happens to be the same as this value here. So for whatever the mean of our population is, our sample means will also have that same mean. So this is our mean here of our samples. So let's have a look then at standard deviation. This is our standard deviation of our population. Our standard deviation of our sample means will be given by the standard deviation divided by the square root of n, where n is the sample size. And this is the standard deviation of our population here. So this is also called the standard error. So it's the standard deviation of our sampling distribution of our sample means. It's just called the standard error. So what about the distributions themselves, the shape of the distributions then? Well, whatever shape our population is, whether it's normally distributed, whether it's kind of right skewed, if you like, that's right skewed or positively skewed, or if it's left skewed or negatively skewed. If our sample size if n is greater than or equal to 30, then the sampling distribution of our sample means will be normal. It will always be normal. So whatever our population distribution looks like, our sample distribution will be normal, providing our sample size is greater than or equal to 30. Now, if our sample size is not greater than or equal to 30, if n is less than 30, then this really only works when our population distribution is normal. If our population distribution is normal, then all of this above applies. Our mean will be the same as the mean of our population. Our standard deviation will be given by standard deviation of our population divided by the square root of n. So it works even if the sample size is less than 30, but our population distribution must be normal. For sample size is greater than or equal to 30, it doesn't really matter what the population distribution looks like. It can be right skewed, left skewed, or normal, but our sample means distribution will be normal. And that's basically the central limit theorem.